So we come to this topic of capacitors, and I'm making this lecture with a special purpose because we have missed 1 week and we got to make this up. So here is a complete lecture on capacitors with problem solutions at the end of it. Okay, so what is a capacitor? A capacitor basically stores electrical energy. And it has a wide range of uses. Okay? What we see here is actually a parallel plate capacitor. So we have two plates that are kept parallel to each other with just maybe air between them. And air is an insulator. In this case, it's called a dielectric. So you have two metal plates with air separating them. And typically the distance between them is really small. So the plates have a certain area and they are separated by a certain distance. And there is an insulator between them. So that's the basic construction of a parallel plate capacitor. And when you connect this capacitor to a battery, the plates get charged. The plate that is connected to the positive terminal gets positively charged, and the plate that's connected to the negative terminal is negatively charged. So this plate becomes positively charged, and this one becomes negatively charged. The actual construction of a parallel plate capacitor is shown by the side, where you have two aluminum foils, and between them you have paraffin paper or mica, and it's rolled up. Now, the advantage of doing that is to make the area as big as possible. So when you look at a parallel plate capacitor, practically you would see it as a cylinder, because that's what you would see. It's rolled up into a cylinder and then put inside a metallic protective casing. But basically, it's two parallel plates separated by an insulator. So what are the uses of capacitors? So as I said, capacitor stores electrical energy, and it stores electrical energy in the form of an electric field. So it's a device that stores electrical energy as an electric field. What are the uses of capacitors? Capacitors are used in computer keyboards, which is the best application that comes to mind, where you hit the keyboard and you're actually changing the distance between the two plates, causing a change in the electrical circuit. They're used in defibrillators. They're used in filter circuits where you want to remove the ripples, where you want to make it convert completely into DC from AC. Camera flashes, of course, use huge capacitors. Motors have capacitors with them. An air conditioner has a capacitor with it because it's a compressor, rather it's a motor kind of thing. So capacitors have a wide range of uses. So let's look at how a capacitor works. The basic formula for a capacitance is it is the ratio of charge to the voltage. C is capacitance, Q is charge, and V is volts. And the units are farad is equal to coulomb per volt. Now there's a basic question that comes about here, like if you're asked, hey, if the charge given to a capacitor is increased, so Q is increased, what happens to the capacitance? Now most students are compelled to say the capacitance also increases, because they're looking at it mathematically. But the answer is the capacitance stays the same, because capacitance is a constant. It does not depend on the charge. So mathematically, how do you explain that? Mathematically, the charge is proportional to the voltage. So if the charge is doubled, then the voltage is also doubled. So the ratio is the same. The charge is tripled, the voltage is tripled. Again, the ratio is the same. So remember that capacitance of a particular capacitor is a constant. It only depends on the geometry of the capacitance. As we're going to see later, it depends on the area of the plates, the distance between the plates, and the nature of the insulator between them. So it depends on its geometry, it depends on its construction. Capacitance is a constant. So that's very important to know. So here is the computer key. You can see that the bottom plate is fixed. The top plate is movable. When you hit that, the distance changes, and therefore there is a small change in the electrical circuit. On the right side, you see the different types of capacitors. There are ceramic capacitors, electrolytic capacitors. Also remember that capacitors, they may have a polarity. So when you connect them in an electrical circuit, one has to be connected to the positive side and the other to the negative side. That is true if it's an electrolytic capacitor. But most of the time, capacitors do not have a polarity, so you can connect the plate either way. We'll get to all that, but let's now find the formula for capacitance of a parallel plate capacitor. So what you see there is a parallel plate capacitor connected to a battery. The left plate is positively charged, the right one is negatively charged, and so it sets up an electric field between them. We know that the electric field is always from positive to negative, so it's from left to right, from the positive plate to the negative plate. And the charge on the plates will be the same. We are assuming that it's a symmetric arrangement with the area of the plates being the same. So when the charge on both the plates are same in magnitude, we can define the surface density of charge, sigma. Sigma is charge by area. So that's what you see. Sigma is Q by A. And sigma is the same in magnitude for both the plates. We have already derived the formula that when the distance between the plates is small, we find that the electric field is given by sigma by epsilon naught between the two plates. So E is sigma by epsilon naught. So it doesn't depend on the distance between the plates. And then we know that electric field is also defined as V by D. So we can now substitute, we can say voltage is E times D, but E is sigma by epsilon naught, and then you get QD by epsilon naught A. That is the voltage. Simple substitutions there. So once we get the voltage, we can find the capacitance, because capacitance is Q by voltage. And voltage is there, so substitute that. Of course, it flips, and then you get epsilon naught A by T, which is the formula for the capacitance of a parallel plate capacitor with air as the dielectric. Now remember, epsilon naught is the permittivity of free space or air. A is the area of the plates in meter squared. D is the distance between the plates in meter. But instead of air, if we have another material there between the plates, then the formula changes to epsilon naught K A by D, where K is called the dielectric constant. It just shows how many times bigger the permittivity of the material is compared to air. So you just got to have, it might be 2, 3, 4. It's just a number without any units. So remember that. K for air is, of course, 1. Now here is a question, simple one. The area is taken as 1 meter squared. D is 1 millimeter between the plates. And epsilon naught is 8.85 times 10 to the negative 12. So you see in the denominator, in place of millimeter, 1 millimeter, you have 10 to the negative 3 meter. That's 1 by 1,000. And then when you do the calculations, you get 8.85 times 10 to the negative 9 farad. 8.85 times 10 to the negative 9 farad, which is 8.85 nanofarad. Because 1 nanofarad, remember nano, 9, is 10 to the negative 9 farad. So that's how we get that. Next, let's look at a spherical capacitor. So we have to now find the formula for capacitance of a spherical capacitor. You see that it's one sphere inside the other. The radius of the sphere inside is R1 and the outer one is R2. And if the outer one is given a charge which is negative Q, then by electrostatic induction, the inner one attains an equal positive charge. So it's minus Q on the outer one and plus Q on the inner one. All right, so and to find out the capacitance, we are going to use Gauss's theorem. So you can already see the Gaussian surface given by the yellow dotted line there. That is the Gaussian surface, which you see here. Gaussian surface is a sphere again. And we are going to use that to find the capacitance. So let's apply Gauss' theorem. And what is Gauss' theorem or Gauss' law? The total flux, electric flux, passing through a closed surface is 1 by epsilon naught times the charge inside the surface. Therefore, you can mathematically, it is closed surface integral E dot dA. Closed surface integral E dot dA is equal to Q by epsilon naught, right? Where Q is the charge. And when we use that here, because the Gaussian surface is a sphere and its radius is taken as a little r, the surface area is 4 pi r squared. So E is a constant at every point on that Gaussian surface. The radius of the Gaussian surface is r. Therefore, its surface area is 4 pi r squared. And that's why on the left side you have E times 4 pi r squared. And the right side is Q by epsilon naught. Now this can be written as 1 by 4 pi epsilon naught Q by r squared. I just took the 4 pi to the other side and rearranged it. Now, voltage between the two plates is defined, or potential difference is defined as integral R1 to R2 E dot dr. Okay, that's the fundamental definition of potential difference, because potential difference is the work done in taking a +1 coulomb from the inner sphere to the outer sphere, all right, against the forces of repulsion. So that's why we have integral R1 to R2 E dot dr. Then substitute for E, which we have, which is 1 by 4 pi epsilon naught Q by r squared dr, and then do the integration. The constants are taken out. 4 pi epsilon naught and Q are constants. So that can be taken out. So Q by 4 pi epsilon naught, and you have integral dr by r squared, which is actually r raised to minus 2 dr. Integral r raised to minus 2 dr, you get it as 1 by r. And then when you substitute the limits, you get 1 by r1. Actually, it should be 1 by r2 minus 1 by r1, because r2 is greater than r1. So it's 1 by r2 minus 1 by r1. And then capacitance is Q by voltage. So you divide the Q by the whole voltage which we have, and then mathematically you see that the Q's get cancelled, the 4 pi epsilon naught flips, and then you have R1 R2 by R2 minus R1. How do you get that? That's when you take the lowest common multiple of 1 by R1 minus 1 by R2. You know, it's R2 minus R1 by R1 R2. So now let us take a look at the cylindrical capacitor. So in a cylindrical capacitor, you have one cylinder inside nether. Okay, so you have one aluminum cylinder inside nether. So they have different radii given as R1 for the inner cylinder, R2 for the outer cylinder. And again, when you give the outer cylinder a particular charge, the opposite kind of charge by electrostatic induction appears on the inner one. So they have equal charge but opposite. And then in this case, the Gaussian surface given by the yellow dotted line is a cylindrical surface. And that cylindrical surface has a radius little r, as you can see, and the length of that surface will be the length of the cylinders. Okay, so that's the Gaussian surface. And we're going to apply Gaussian theorem again. And according to the Gauss theorem, integral E dot dA is Q by epsilon naught. But in this case, dA is the area of the Gaussian surface, which is 2 pi r times the length. Because 2 pi r is the circumference times the length gives you the surface area of the Gaussian surface. That's why we have 2 pi r times L. So when you rearrange that, you take 2 pi RL to the other side, goes to the denominator. We have that. And then voltage, again, is defined as the work done in taking this charge from R1 to R2, plus 1 coulomb, right? Just like before. And that's E dot dr. So substitute the value of E. E is Q by 2 pi RL epsilon naught. Take the constants out. The only variable is R, and that's inside. So you have integral R1 to R2, 1 by R dr. Okay. What is integral 1 by R dr? It is the natural log of R. Yes. Integral 1 by x dx is natural log of x. So that's why in the next step, you have those constants. And then you have natural log of R2 by R1, which is what you get after you substitute the limits. R2 is the upper and R1 is the lower limit. Okay, so natural log of R is what you get. And then it'll be natural log R2 minus natural log R1. But you know that log A minus log B is log A by B. Right, a little bit of math there. So the difference becomes a ratio. And then finally, capacitance is Q by voltage. So the Q will get cancelled when you substitute the entire value for the voltage. This is going to flip and you get this as the final formula. Again, how do you increase the capacitance? Well, decrease the denominator. That means make R2 by R1 as small as possible, which again means the gap between them should be small. And also increase the length, because the length of the cylinders is in the numerator. So make the length as big as possible. So that's how you make cylindrical capacitors. So what we have here is an application of capacitors, which is used for tuning a radio, manual tuning of a radio where you turn a knob. So actually what happens behind that is you have a set of capacitor plates. One set of plates is fixed, it can move. The other set of plates is movable. So as you move the knob, you're actually turning the movable capacitor plates and making them go into the stationary plates. So the overlapping area here increases. And as the area increases, the capacitance increases. Okay, so that's how, when you change the capacitance, later on we will see that the frequency received by the radio changes. So this is a very important application. So that's where you see the rotor, which is fixed, and the stator, the stator that is fixed and the rotor that moves. So that's what you see. It's called a gang condenser, because there's a lot of plates. Okay, it's a variable air capacitor. It's a set of plates. Let me run this through. A set of plates, rotatable. As the overlapping area changes, the capacitance changes, because capacitance is epsilon naught A by D. And it's used in tuning a radio. So that is what we have there. The next topic is where we combine capacitors. You connect many capacitors together. And capacitors can be combined in series and in parallel. And there are obvious reasons as to why we need to combine them. It's not just to change the capacitance. So we will see that after we look at the combination of capacitors. So let's go there now. Okay, so before that, here is the symbol for a variable capacitor. On the left side, if you have an arrow passing through it, it means it's a variable. That means its value can be changed. But on the right side, because you see one plate bend, that is the symbol for an electrolytic capacitor. Okay. So here is the combination of capacitors that you see on the right side. So there are three capacitors. Their values are C1, C2, and C3, and they are connected in series to a battery of voltage V volts. So as a result, what happens is, whatever be the value of the capacitors, they all get equally charged. So this is very important. So C1, C2, and C3 may have any values. One may be small, the other may be big, but no matter what, whenever you connect capacitors in series, they get equally charged. So let Q be the charge on each capacitor, as you can see in the diagram. And then the voltages across each capacitor will not be the same. It'll be V1, V2, and V3. But when you add those three voltages, you must get the source voltage. I hope that makes sense. Which means, in place of these three capacitors, we could have a single capacitor, which is called the equivalent capacitance. So that's what you see on the right side. You see a single capacitor which accumulates the same charge Q as before, and of course the voltage is V because it's connected to the same battery. Therefore, now we are trying to find the formula for equivalent capacitance. What do we need to do? Okay, like I said, what's important is to remember that the charges are equal, but the voltages are different. Voltage means potential drop, potential difference. So that's important. And then V1 plus V2 plus V3 should give you the source voltage. But what is V1? It's Q by C1. Similarly, V2 is Q by C2. Okay? And then on the right side, Q by C. The Q's cancel out. So you have 1 over C is 1 over C1 plus 1 over C2 plus 1 over C3. This is the formula used to find the equivalent capacitance of capacitances connected in series. Remember, C sub S is what we're looking for. So when you do the math, remember on the left-hand side is 1 over C sub S. So many students forget to flip it. Many students forget to take the reciprocal of that. So don't. Please take the reciprocal, okay? Don't forget. Now, on the other hand, if capacitances are connected in series, you know that the equivalent capacitance is going to be smaller than the smallest of the three, or the smallest of any number you have connected. Just a point to remember, CS is going to be small. So, for example, if C1 is 1 microfarad, C2 is 2 microfarad, and C3 is 3 microfarad, okay? CS is going to be less than 1 microfarad, because 1 is the smallest amongst them. Okay, so now let's look at the other combination. That is when you combine them in parallel. When you combine them in parallel and they are connected to the voltage source individually, you can see that each set of plates is connected to the voltage source individually, which means the voltages will be the same. So whenever electrical components are connected in parallel, the voltage across them, the potential difference across them will be the same. But now the charges will be different. You see, it's exactly opposite of the series combination. The voltage will be the same, but the charges will be different. And therefore, we can now replace these three capacitors with a single capacitance as shown below. And the charge on that capacitance must be the total charge of all the other three. So that's why Q is shown as Q1 plus Q2 plus Q3. Okay? And let's work out the formula. So important point, remember, the voltages are same in parallel, but the charges are different. And again, the total charge is a sum of the individual charges. But what's the formula for charge? Isn't charge just the product of capacitance and voltage? Yes. So that's why we have this. And the voltage gets cancelled. And you get C parallel is simply the sum of the capacitances. So that's easy. Whenever capacitances are combined in parallel, to get the equivalent capacitance, just add the values of the capacitances, which again shows that in this case the equivalent capacitance will be bigger than the highest amongst them. So for example, if it's 1, 2, and 3 microfarad, of course the equivalent capacitance is 6 microfarads, right? Which is bigger than 3, okay. All right, so here you have an application of capacitance. You have the stud finder, and you see that the simple idea is that when you have a material, see the capacitor plates and you're moving that material, and as you move the stud finder, the material between the plates changes, and when that changes, the capacitance changes, giving us a signal. So it can find the difference between wood and metal. Okay, wood and empty space. You know, between the studs you have the empty space. You're looking for the stud. So when we reach the stud, you have the wood between the two plates. The capacitance has a different value compared to when you have the gap or the air between them. So that's how this stud finder works. That being said, here is a table that gives the dielectric constants. Those are the K values. Vacuum or air has approximately 1, and you see paraffin as 2.2, and as you go down, paper has a dielectric constant 3.7, and the mica has 7. What do you mean by dielectric constant? Simply, if you have air as the dielectric, and then you replace the air with mica, as an example, you're not changing the other geometry, like you're not changing the area of the plates, not changing the distance. You simply filled it with mica. That means the capacitance now becomes 7 times of what it was with air. Hope that makes sense. So when you insert the dielectric, the capacitance increases to as many times as the dielectric constant. So if you have paraffin, then the capacitance is 2.2 times that with air. If you have mica, it's 7 times that with air. Now, that's not the only advantage of using a dielectric between the plates. You can also see that the dielectric strength. Now, what do you mean by dielectric strength? It's given in volt per meter. It gives the point at which the dielectric stops functioning as a dielectric. Remember, it's an insulator. And when you apply too much of a voltage per meter, or you apply too much of an electric field, the dielectric breaks down. It loses its insulating properties. And we're going to look at this in detail, but just remember that for mica, as you can see, the dielectric strength is 150 times 10 to the power 6. 150 times 10 to the power 6 volt per meter. So you see, it did not only increase the capacitance, it also gives it a much higher dielectric strength. So that's why we use dielectrics in capacitors. All right. Cut. action. Now we're going to look at the meaning of electric polarization. Now, electric polarization is what happens to the molecules of the dielectric kept between the two plates. So there are, that in atoms the positive charge is in the nucleus and the negative charges are the electrons. Usually the center of the negative charges and the center of the positive charges, they coincide. So they're exactly at the same point. So in a normal atom, not only are the positive and negative charges equal in magnitude, they also have the same centers. So it's like total cancellation. But when you take this atom and keep it in an electric field, the center of the positive charge goes in the direction of the field, and the center of the negative charge goes in the opposite direction. So when I say it moves, it's a minute movement. It's an atomic movement. They slightly move. And that creates an electric dipole. Remember an electric dipole where the positive and negative charges are separated by a short distance? That is created. Now this is why it's called polarization. The poles are separated. So in the diagram, you see the unpolarized atom on the left side, and then you see the polarized atom on the right side. Well, it's highly magnified. You see that the external, the charges have separated, and then below you see the positive and the negative separated. Okay, so outside you see the charges, that's the electric field, the positive and the negative outside, but inside you see what has happened to the atom. And did you notice that they are opposite to each other? Of course, they're opposite. So inside the dielectric, there's always an electric field that is opposite to the applied electric field. Let me try to say that again. So you have an applied electric field, let us say from left to right, and you keep a dielectric in that field. It sets up a field inside it, which is in the opposite direction. So to find the total field, we have to take the difference between them. We're going to look at all that. So we have the polar molecule. We have the dielectric polarization that I just explained. And then all these diagrams here show you what I was just telling. On the left side, you have the applied electric field. The second diagram shows you what happens to the molecules of the dielectric. You see that the positive and the negative are separated, with the positive moving towards the negative plate. So the field is opposite. Now in the third diagram, you see the direction of the field. And again, the fourth one shows you that the induced field, you see E sub IND, the induced field is opposite to the applied field. Okay, so again, diagrams A and B show you the same thing, You see that the fields are opposite. So finally, let us derive a formula for energy of a charged capacitor. So we want to calculate how much energy is stored in a charged capacitor. Whenever we try to find energy, we always think about work, because energy is the ability to do work. Whatever is the work done in charging the capacitor is the energy stored by the capacitor. Just like, remember, the potential energy of an object in the gravitational field is the work done in lifting it, right? Same way. And what is work? Work in terms of potential. Remember, potential or voltage is work over charge. Voltage is work divided by charge. I'm going to show you. And so work would be the product of voltage and charge. Let's go that route. Let me show you. The small work done is integral V dq. That is by the definition of voltage, because voltage is work over charge. Therefore, work is the product of voltage and charge. And then you have to integrate. And before we integrate, let's substitute for voltage. What is voltage? Voltage is Q by C, isn't it? Q by C, where C is the capacitance. And this integral is to go from the lower limit, which is 0 charge, to the maximum charge. So 0 to caps Q. So we started with no charge on the capacitor, 0, and then slowly but surely the charge increased to caps Q. Whenever you integrate, you take the constants out. The constant is 1 over C. That's taken out, and then you have integral Q dQ, which is Q squared by 2. And then when you substitute the limits, you're going to get Q squared by 2C, because the lower limit is 0. So that's one formula for work done or energy of a charged capacitor. But we can substitute for Q and get another formula. Q is C times, okay. Remember that the symbol for potential energy is U. And then when you say C, it's just potential energy of a capacitor. So U sub C. And then you substitute for Q as CV. And then you will get 1/2 CV squared, or we can substitute for C and get this formula as 1/2 Q times V. So there are 3 formulas which could be used to calculate the energy of a charged capacitor. It's Q squared by 2C, 1/2 CV squared, just like 1/2 mass times velocity squared, just to remember, or half times Q times the voltage. And what formula you're going to use depends on what is given. So that's why next we're going to do problems, work out some problems. And these problems are going to be very important, where you're going to see how the formulas that we derived can be applied to calculate certain quantities. So let's go there. So let's work out these problems. And this is taken from a previous quiz. So here is the first question. A cylindrical capacitor is made of 2 concentric cylinders. The inner cylinder has radius R1 as 4 millimeter. The outer one has a radius R2 is 8 millimeter. And what's that? The common length of the cylinder is 150 meter. That's huge. What is the potential energy stored in this capacitor when a potential difference of 4 volts is applied between the inner and outer cylinder? So it is a cylindrical capacitor, and we are asked to find the potential energy stored in this capacitor. We know that the potential energy can be calculated in 3 ways. One of the formulas is 1/2 CV squared, and the voltage is given 4 volt, but we have to find the capacitance first. So let's do this. Let's first find the capacitance of the parallel plate capacitor. Okay, so the potential difference is Q by 2 pi epsilon naught L natural log R1 by R2, or RA by RB. That's a formula for voltage. And then charge from that is 2 pi epsilon naught L natural log RA by RB. Just rearranging that, So 2 times a pi, which is 3.14. Epsilon naught is 8.85 times 10 to the negative 12 times the length is 150 meter, and then natural log RA. You can keep it in millimeters because it's a ratio, so 8 by 4. So I found the charge, and then I'm going to use 1/2 Q times V. You could have found the capacitance and used the other formula. You would get the same result. But I found the charge on the capacitor, and then used the formula for potential energy, which is 1/2 times, looks like I made a calculation mistake there. Oh, I forgot to multiply it with voltage, which I corrected now. Okay, you see the 4, the voltage, I forgot that. And so now I got the answer as 9.6 times 10 to the negative 8 joules. Let's go to the second one. Here's the second question. The capacitance per unit length. You see that? So that's per meter. So the length is given as 1 meter. The capacitance per unit length of a coaxial cable made of 2 concentric cylinders is 50 picofarad per meter. What's the radius of the outer cylinder if the radius of the inner one is 1.0 millimeter? Again, a cylindrical capacitor, and the capacitance is given. We're asked to find the radius. So go to the formula for a capacitance of a cylindrical capacitor, which is C is 2 pi epsilon naught times the length, natural log inner radius by outer radius. So that actually it's outer radius by inner radius, right? Or A is the outer one, B is the inner one. So when you rearrange that, we're trying to look for the radius of the inner one. So remember that. So when we do that, you get 2 pi epsilon naught by C by L. Remember, I separated C by the length because that's what is given, picofarad per meter. And then do the calculations, you get RA, which is what we're looking for. RA is 3.04 times RB, which is 3.0 millimeter. So, the radius of the inner one is 1 millimeter, so the radius of the outer one is what we are looking for. So that is 3.0 millimeter. Hope you look at that math and work it out. But what is important here is what is given is not just the capacitance, it's a capacitance by length because of the units picofarad per meter. So be aware of that. Here's a third one. A parallel plate capacitor, now it's a parallel plate capacitor, has a voltage, 6 volt between its plates, and each plate carries a surface density sigma is 7.0 nanocoulomb per meter squared. What is the separation of the plates? So we're looking for little d, and we're given the voltage. Okay. So for a parallel plate capacitor, this is the formula, epsilon naught A by D, but capacitance is charged by voltage, and you know sigma is Q by A, so Q is sigma times A. So I'm substituting that, and I'm getting C is sigma A by voltage, so I can substitute it in place of C, which is sigma A by voltage is epsilon naught A by D. And then the A's get cancelled, and you make D the subject, you get epsilon naught V by sigma. And then it's a matter of substitution. So that's epsilon naught. The voltage is given as 6.0. Sigma is given. So 7.0 times 10 to the negative 9. So it's the ability to manipulate these quantities by knowing the relation between these quantities. So D, is going to be really small. It's 7.6 millimeters in this case. So that's problem number 3. Let's go to the next one. Problem number 4. A parallel plate capacitor with a plate separation of 4.0 centimeter. That's big. It's separated out. This could be a setup in the lab. That's why it's that far away. Has a plate area of 6.0 times 10 to the negative 2 meter squared. What is the capacitance of this capacitor if a dielectric material with a dielectric constant of 2.4 is placed between the plates? That is a direct question. We just have to find the capacitance. So here's the formula for capacitance, which is what? Epsilon naught K, epsilon naught A by D, K, epsilon naught A by D. K is the dielectric constant, 2.4. Area must be in meter squared, which it is. Epsilon naught is 8.85 times 10 to the negative 12. And by D, which is the separation, but it has to be in meter. So that's why I've changed it. And you get the answer as 32 times 10 to the negative 12 farad, which is actually 32 picofarad. So that is the answer. So here is problem number 5. A parallel plate capacitor has plates of area 0.80 meter squared separated by a distance of 3.0 millimeter. What is this capacitor's capacitance? Okay. What is the dielectric in this case? The dielectric, if nothing is mentioned, is by default air. And what's the value of K? It's 1. So simple enough question. C is K epsilon naught A by D. K is 1. Nothing is mentioned. That means it's air. And then all you got to do is substitute the values of epsilon naught and area and D and do the calculation. 0.80, but the distance is in millimeters, so you got to change it into meter. And we get it as 2.4 times 10 to the negative 9 farad. All right, here is the next question. Don't worry about the number because it's just picked at random. So, a system of capacitors is connected across a 90-volt DC voltage source. So that's how you represent a voltage source, a DC voltage source as shown in the figure. What is the equivalent capacitance of the system? Take a look at this. The 2 microfarad and the 4 microfarad on top are connected in series. Similarly, the 3 and the 6 below are also connected in series. But these two combinations are connected in parallel. So if once you get that, you can figure it out. Okay, so how do we calculate that? Oh, I'm drawing the diagram again just to show you the arrangement. And that is what is given. 90 volt, this is 2. You have 3 below, 4 and 6, all in microfarads. And then the 2 is in series with 4. I'm actually writing it down so you understand, which means C is C1 C2 by C1 plus C2. Okay, that's a shortcut that you could use, but it only works for 2 capacitors. Remember, we had to use 1 over C is equal to 1 over C1 plus 1 over C2. But instead of that, we can use C1 C2 by C1 plus C2. Just take the product, divide by the sum. Product divide by the sum whenever capacitances are in series. That's a shortcut. So that gives 8 by 6. And that is 4 by 3 microfarad. Do the same with the other combination because the 3 is again in series with 6. So 3 times 6, 18 divided by 3 plus 6, 9. And then because they are parallel, now you got to add them. That's it, because when they are in parallel, you just add them, don't you? And the final answer is 3.3 microfarad. Remember, I kept it in microfarad throughout. You need not change the unit, just leave it in microfarad. Brings us to the next one. A charge of 2 microcoulomb flows onto the plates of a capacitor when it's connected to a 12 volt battery. How much work was done in charging this capacitor? The work done in charging the capacitor is nothing but energy. So in other words, you have to find the energy of this capacitor. Okay, work done is energy, potential energy, which is 1/2 Q times the voltage. Remember, there are 3 formulas. Use the one that is applicable at that point. In this case, charge is 2 micro. That's why it's 2 times 10 to the negative 6. The voltage is 12. So when you do that, you're going to get 12.0 times 10 to the negative 6 joules, which is actually 12.0 microjoules. That's the next one. All right, number 8. A metal cylinder of radius 2 millimeters concentric. What do you mean by concentric? That means the centers coincide. So one cylinder is kept inside another, but their axes coincide. The space between the cylinders is filled with air, and the length of the cylinders is 50 centimeter. What is the capacitance of this arrangement? Again, a cylindrical capacitor, so we've done this before. We know that the formula for capacitance of a cylindrical capacitor is what? 2 pi epsilon naught L by natural log or A by RB. A is the outer one, B is the inner one. Everything given here, so it's just math. 8.85 times 10 to the negative. I know it's just math, but you got to be careful. The length is 0.5 meters because it's 50 centimeter. And then when you take the ratio, it could be in millimeters. As long as the radii are in the same units, don't worry. Just put them there, it's the ratio. And you get 30 picofarad. 30 picofarad. All right, the next one. A parallel plate capacitor has a capacitance of 10, what is that? Millifarad, and is charged with 20 volt power supply. Okay. So the capacitance is given and it's charged with a 20 volt power supply, which means the capacitor gets charged to a voltage of 20 volt. The power supply is then removed and a dielectric of dielectric constant 4 is used to fill the space between the plates. The voltage now across the capacitor is, wow, we've got to be careful here. When you disconnect the battery, the charge on the capacitor stays the same. It has no place to go. So whatever charge it had when the source was connected would still be the charge. So the charge doesn't change. But when you introduce, what do you do? The power supply is removed and that dielectric is introduced, isn't it? Yeah, used to fill the space. So when you bring in the dielectric, the capacitance changes. Or here again, the charge stays the same because it has no place to go, no connections. But when you introduce the dielectric, the capacitance has increased, which means the voltage decreases. And you're asked to find the new voltage. When we work it out, you should understand. Okay. So on charging, Q, we're trying to find the charge because we know it stays the same. Charge is the product of capacitance and voltage. 10 milli. Milli is 10 to the negative 3. Okay, times 20. So you got the charge. And then on removing the dielectric, are we removing? No, removing the source. Yeah, on removing the power supply or the source. That is coming so slowly. And I said this like a couple of times. The charge remains constant. In other words, it does not change. So we know the charge, but the capacitance increases. Yeah. And it increases 4 times because the dielectric constant is 4. The dielectric constant being 4, the capacitance increases to 4 times. Without doing this, we could know that means the voltage decreases 4 times. We could actually do it without the math. We could just say, oh, 20 volt became 5 volt. But you can also get it mathematically for those who are so fond of math, which I am too, by the way. And you get 5 volt. So take a look at this question. And there are different versions of this question. In the sense that if you had, got to be careful when I ask you this. If instead of disconnecting the battery, we had left the battery there and then introduced the dielectric while the power supply was still connected, what would happen? Give it a minute. So you introduce the dielectric while the power supply is still connected. Yes, the capacitance would increase to 4 times, but in this case, the voltage cannot change. The voltage has to be 20 volt. It's still connected to the source, so the voltage can only go up to what the source voltage is. All right, so the capacitance increases, the voltage stays the same, which means what? The charge on the capacitor will increase. Yes, when you introduce the dielectric, the plates will get more charged. It'll get charged to 4 times higher than what it was before the dielectric was introduced. So look at the variation. So the point at which you introduce the dielectric is important. If you introduce the dielectric after the power supply is disconnected, then the voltage decreases. But if you introduce the dielectric while the power supply is still connected, then the voltage doesn't change, but instead the charge increases to 4 times. It's going to be a definite question on any exam, So you be careful on understanding this. All right, that's a pointer. So the next one, number 10, a 2 and a 4 microfarad capacitor are connected in series with an 8-volt DC source. What's the charge on the 2 microfarad capacitor? What do we know about a series combination of capacitors? We know that the charge on both will be the same. Yes. So whatever is the charge on the 2 microfarad will be the charge on the 4 microfarad. So that's what we're asked to find. But to do that, we have to find the equivalent capacitance. Okay, let's do it. They are in series. So in series, we use 1 over C is 1 over C1 plus 1 over C2, or the shortcut C1 C2 by C1 plus C2. Keep both in microfarads. So 2 times 4 by 2 plus 4. It gives 8 by 6, 4 by 3 microfarad. Okay, I left it at 8 by 6. And then find the charge by using this capacitance into voltage. That's all. That is 64 by 6, which is 11 microcoulomb. So because I have the capacitance as microfarad multiplied by voltage, you're going to get 11 microcoulomb. Be careful about that. Okay, so that is the charge on both of those capacitors. 2 more questions to go. Here is the 11th one. What charge appears on the plates of a 6.0 microfarad capacitor when it is charged to 40 volt? Oh my goodness, this is so easy. Charge is just the product of capacitance and voltage. So that's in microfarad multiplied by voltage, 40 volt, gives you 240 microcoulomb. Brings us to the last question. Here's the last one. A parallel plate capacitor has a voltage 2 volt between its plates. Each plate carries a surface density sigma 8.0 nanocoulomb per meter squared. What is the separation of the plates? I think we did something similar to this. All right, let's do this. Sigma is Q by A. E is V by D. All of these relation. And then, I'm not using that. I'm just going with E is equal to V by D, sigma by epsilon naught, from which D is what? 2.0 times 8.85 times 10 to the negative 12 by sigma. I noticed that sigma is directly given, so there was no need of using the other one. Just straight away, get the distance between the plates. Remember, the distance between the capacitor plates is always small, so when you get the answer, it must be small. Okay, so get 2.2 millimeters. Well, this is a video that I've made taking a lot of time, because of this loss of 1 week. And so you have to prepare well using the lecture and look at how the problems are worked out. Capacitance is a big topic and an important topic. I'll be summarizing this in class, but here is how you get the detailed version. Thank you, and we'll see you all on the next video.